Hello everyone, welcome to my channel Master Computer Science Subjects. This video is in continuation with the previous video. In the previous video we have seen pass 1 design of assembler. Now in this video we are going to see the pass 2 design of assembler. Okay, just we recollect the functions what is being performed by assembler during pass 2. It starts assembling the instruction. It means every instruction is translated into object code. And if data values are there in the program, the corresponding hexadecimal values are also generated. And if any of the assembler directives is missed to be processed in pass 1, that will be processed during pass 2. Finally, the object program will be written. So these are the functions of assembler during pass 2. Right. Before starting to translate the program into object code, let us recollect these things. From the instructions or by looking into the instructions, we should be able to tell what type of addressing mode it belongs to. If there is a memory reference in the instruction, it can be either PC relative or base relative. Okay, how can we confirm it is PC relative or base relative? When you calculate the displacement value, if it lies within this range, then it is PC relative. If the displacement value is not lying in this range, then we should think of base relative. For base relative, displacement value must be in this range, 0 to 4096. Okay. If at symbol appears in the operand column of the instruction, then it is indirect. Hash symbol appears, it is immediate addressing mode. If there is a plus sign appears before the mnemonic, it is format 4 instruction. If X is one of the operand, it is indexed addressing mode. And the combinations of addressing modes also happen. Right. Now, let us continue with the same example, what we have done during pass 1. Right. This is a program we solved during pass 1. During pass 1, we just incremented the location counter as per the format of the instruction or as per the length of the instruction. Now we are going to start with the format 2. See, please look into the instruction which I have written using red color. So, right. So this is the instruction. Clear is the instruction. X is available at the operand. Right. This is format 2 instruction. If it is format 3 instruction and if X is one of the operand, then we can think of indexed addressing mode. But clear is a format 2 instruction. Right. Format 2 instruction is having this structure. We have 8-bit opcode for register 1 4 bits, for register 2 4 bits. Totally it is 16 bits length. For clear, the opcode is B4. So how do I write this B4 here? B is equivalent to 11. So I will write like this. 1 0 1 1. For 4 we have to write 0 1 0 0. Then the register what is referred in the instruction is X. For X, already we know what is its mnemonic value. Its mnemonic value is 1, which is already pushed into the symbol table during pass 1. A is 0, X is 1, L is 2, B is 3, S is 4, T is 5, F is 6. So for X it is being given as 1. That is the hexadecimal address of X register that I am going to write here in binary format. 0 0 0 1. Since there is no register reference here, by default we will write it as 0. So now let us write the object code for this instruction. Combine from the LSB position 4 bits and write its hexadecimal equivalent. For this 0 0 0 0, the equivalent is 0. 0 0 0 1, the hexadecimal equivalent is 1. This is 0 1 0 0, it is 4. For this instruction for this 4 bits, the hexadecimal equivalent is B. So this instruction clear X, the corresponding object code is B410. So let me enter here. B410 is a corresponding object code which is written in hexadecimal for the instruction clear X. Okay, now let us move on to the next instruction, LDT length. So I have written here. Please observe whatever I have written using red. LDT length is the instruction. So LDT is a mnemonic or the operator. And this instruction is available at the address 405F. This is the starting address of this instruction. Okay, what is the opcode for LDT? It is 74. For 7, this is the binary equivalent. For 4, this is the binary equivalent. Okay, now let us build the object code for this. Let me write the opcode here. This is the format 3 instruction format. 6 bits is opcode, then 6 single bit information we have, N, I, X, B, P, E, then finally the 12 bits is for displacement. Already we have discussed about instruction formats of SICXC in my previous video. You can refer to that video also. Okay, how do we write the opcode? But in fact the opcode length is here 8 bits. But here how many bits is given here? Only 6 bits is given here in the opcode section. So how do I write this opcode? Let me write 7 0 1 1 1 as it is. Then for the 4 0 1 0 0, I'm going to write only these 2 bits. I'm going to leave these 2 bits. So let me write a 0 1 here. Right. We filled the opcode. Okay, what is the information for this NIXBP? Since it is format 3, the value of E is equal to 0. If it is format 4, the value of E becomes 1. And from the instruction, we can know that it is neither indirect nor immediate. If it is not indirect or not immediate, the invalidity of N and I should be marked by 1. This also we have already seen in the instruction format. Since the instruction is not involving X as one of the operand, it is not indexed addressing mode also. So let us mark X is equal to 0. So now there is a confusion between B and P. It can be either base relative or PC relative. By default, first we have to assume it is PC relative. Right. If it is PC relative addressing mode, how do we calculate the target address? Target address is equal to PC plus displacement. Okay. Now, what is the target address? That we have to understand. So read the instruction here. The instruction given is LDT length. What is the meaning of this instruction? Load the register T with the content of length. What is length? Length is a memory location. So when the assembler is executing this instruction, to load the value with length into T, it should go to this location. Wherever the length is available, the assembler has to go to the location. So this is the target address. Already in the question itself, the value of length is being given as 4036. So length is the target address. So I have written here as 4036. What is the value of PC? Program counter always contains the address of the next instruction to be executed. So now this is the current instruction we are executing now. I mean it is being assembled now. The address of this instruction is 405F. But program counter will be containing the address of the next instruction, which is 4062. Right. So the content of PC is 4062. This is the displacement value. Let us calculate the displacement value. Displacement is equal to 4036 minus 4062. Remember, these are all hexadecimal. You have to perform hexadecimal arithmetic operation. You can use a calculator just to get into the hexadecimal mode and you can perform the operation. In fact, we are subtracting a larger number from the smaller number. So the difference is minus 2CH. It is a negative number. So I'm finding the 2's complement of that. So how do I find the 2's complement? 2C. But the displacement field, in fact, it is 12 bits. So what I'm writing it as 0 to C. For C, this is a binary equivalent. For 2, this is a binary equivalent. And the rest of the MSB values, I am filling it with zeros. Okay, now I am finding its 2's complement. 0, 0, 1 I have to write as it. This is a shortcut method to find the 2's complement. Start writing the bits from the left, LSB, till you find the first one. Once you found the first one, the rest of the bits and all you keep flipping. You will be getting the 2's complement. So 0, 0, 1 you write. Now 1 is flipped to 0, 0 is flipped to 1. Again, I have written like this. So this is the 2's complement value of minus 2c. So now I'm finding the hexadecimal equivalent for this. This is 4, this is d, this is f. So I know what is the displacement. So let me write the displacement here. 1, 1, 1, 1. D is 1, 1, 0, 1. Then this 4 I am writing as such, which is 0, 1, 0, 0. Right. And I forgot to tell one more information. Why we have calculated the displacement. The hexadecimal difference has come as minus 2 say. Now I'm converting this into decimal value and I'm checking whether it is in the range of minus 2047 to 2048. If it lies within the range, if the displacement value lies within the range, then only we can come to the conclusion it is PC relative. Of course, minus 44 is within the range. So whatever the displacement we have calculated is correct. Now let us find the object code. Already for the instruction LDT length, we have written the opcode. We know what is the addressing mode it refers to. It is not base relative, but it is PC relative. And we have calculated the displacement also now. We have calculated the displacement like this. Now only thing we have to translate this into object code. From the last 4 bits you combine and you write the hexadecimal equivalent. For this 0100 it is 4. For this 1101 it is 8 plus 4 12 plus 1 13, it is D. Yeah, this is F. 0010 it is 2. 0111 it is 7. This is also 7. So the corresponding object code for the instruction LDT length is, let me write it here, 772FD4. This is the corresponding object code for the instruction. Similarly, let us move on to this instruction TD output. Yeah. So this is the instruction. For this only we are going to find the object code now. TD is the operator or the mnemonic. Its operand is output. Of course, this is a label being given and the starting address of this instruction is being given as 4062. For TD, the opcode being given as E0. So let me write the opcode here. Already I have written here in the binary format. For E it is 1110, for 0 it is. So it is 6 bits, right? So 1110 I have written here. Then for equivalent to 0 I am writing only the MSB 2 bits. From the instruction we can come to know it is neither indirect nor immediate. It is not indexed addressing mode also. Since it is format 3 instruction, how do I know it is format 3 instruction? There is no plus here. If there is a plus, it is format 4. Since there is no plus available here, it is format 3. If it is format 3, E value is equal to 0. Once again, there is a confusion between whether it is PC relative or base relative. First, we have to assume by default it is PC relative. So, if it is PC relative, target address is equal to PC plus displacement. So what is the target address here? From the instruction we can come to know when the assembler is executing this instruction, it should go to the memory location by the name output. That is the target address. The target address of output is 4076. We have already inserted the value of output into the symbol table. I'll show the symbol table also. For output, its value is 4076. By the way, we calculated the target address. What is program counter? Program counter always contains the address of the next instruction to be executed. Yes. Current instruction address, address is 4062. Next instruction is this. Its address is being given as 4065. That is why here PC content is written as 4065. We have to calculate the displacement. The displacement is 11. 11. It is written in hexadecimal. Okay, now let us write the object code. 1 is a value, right? But we have to extend it as 12 bits. So right here 0 0 0 0 0 0 0 1 0 0 0 1. It is PC relative. We identified it is not base relative, right? So now how can I find the object code? For this it is 1. For this 4 bits it is 1. It is 0. 0 0 1 0 is 2. 0 0 1 1 is 3. This is E. So E32011 is the object code. Right. Similarly, let us move on to the next instruction. JEQ, jump on equal to the memory location W loop. Its opcode is being given as 30. So let us use this format now. Of course, it is format 3 instruction. 30, how do I write in the opcode column? Very simple. First you write it for 3, 0 0 1 1. For 0, we have to write only 2 zeros. Right. From the instruction, we can come to know it is neither indirect nor immediate. It is not indexed addressing mode also. If it is not index addressing mode, x is equal to 0. If it is not immediate, not indirect, means you have to mark the invalidity by ones. It is format 3, so E value is equal to 0. Again, the the tie is between PC relative or base relative. So first we assume as PC relative. Target address is 4062. The W loop address is 4062, which we have already inserted into the symbol table. I have fetched the value from there. PC is the address of the next instruction. The current instruction address is 4065. We know it is format 3. If you add with this value 3, automatically you will come to know what is the address of the next instruction. So PC value is 4068. If I calculate displacement, again it comes in the negative. So I have done the 2's complement and I have obtained the value FFA. So how do I write this FFA here? 1111 1111 1010, right? It is PC relative, it is not base relative. We confirmed PC relative once again by checking the displacement value within the range. Yes, of course, the displacement value is within the range. Convert this hexadecimal into decimal value, then you check whether it lies in the range. Yes, it is PC relative, no doubt at all. So let us convert this into object code. This 1010 is A, this is F, this is F, then combine these 4 bits. 0010 is 2, 0011 is 3, again 0011 is 3. So the object code is 332FFA. So let me write it here, both the object codes. For the previous instruction, the object code is E32011. For this instruction, the object code is 332FFA. Right. Now, let me do the next instruction. Load character buffer comma x. There is a memory reference and one of the operand is x. So there is a possibility it can be PC relative plus indexed addressing mode. For the load character, the opcode value is being given as 50. So I have entered the value here as for 50101. For 0 we have entered only 00. It is neither indirect nor immediate, so n is equal to 1, I is equal to 1. But it is indexed addressing mode, so x is equal to 1. E is equal to 0 because it is format 3. But I do not know whether it is PC relative or base relative. So as usual, I am trying to calculate the displacement value. But for indexed addressing mode, target address formula goes like this. PC plus the content of x plus displacement. But one of our instructions says that clear x, the first instruction. It means x is cleared to 0. That is why x value is being given as 0. Target address is 4033. So 4033 must be the address of what? Buffer. So I have written here PC is the address of the next instruction to be executed. The next instruction to be executed is this 406B. WD output. So that instruction, that value only is considered as PC value. So I have calculated the displacement and this is the object code I am getting. 53AFC8. Similarly, I assembled the other instructions also. WD output I have assembled. When I assembled this instruction, The object code, whatever I'm getting is, this is 800. 0010 means it is 2. This is F. 13 means it is D. Right? So for this instruction, the object code what we got is DF2008. And TIXR T. This instruction is once again format 2 instruction. For format 2 instruction, this is a format. For TIXR, the opcode is B8. So I have written here 1011. Sorry, it must be written as 1000. So the opcode is B8. The register what it refers to is T and its numeric value is 5. That is why it is written as 0101. There is no value for the other register, so by default it is considered as 0. For this instruction, the object code is B850. So let me write it here, B850. Similarly, the next instruction also, I have already identified the object code. That object code I will enter here. It is also PC relative. As I explained in the previous example, you people please work it out and check whether you are getting the same object code in the hexadecimal format. Okay, I just want to give only this last instruction explanation, written subroutine. This is in fact format 3. So look here how I have written as format 3. For written subroutine, the opcode is 4C. So for the binary information or equivalent is written. For C, the MSB is written 11. It is neither indirect nor immediate. It is not indexed addressing mode. E is also 0. It cannot be PC relative or it can't be base relative also. So accordingly, these values are set to 0. And there is no operator here. So the entire displacement field also is set to 0. When I translate this into object code, this is a value we are getting 0, 0, 0, 0. This 4 ones put together is F and this is 4. 4F0000. This is the hexadecimal equivalent. So the example, whatever I have considered and explained here, mostly involve PC relative addressing mode, and one instruction is indexed addressing mode. And of course, we have two format 2 instructions. So this is a way we have to do the translation and to find the object code. For some of the last some 3-4 instructions, I didn't explain much. I have directly given the object code. You people please try and comment in the comment section. Thank you.